This is the mock solutions for properties of curves. Number 1, the diagram below shows part of the graph of the gradient function y equals f dash of x. So the first thing you need to be careful of is this graph here is not the function f, it's f dash of x. And they didn't even tell us what f looks like, okay? Okay, so first thing you're going to do is you're going to look down here and it says you are going to draw a graph of y double dash of x, clearly indicating the x-intercept. Okay, so we know that if we're going to draw a derivative function from an original function, and basically if we're going to do f double dash, the second derivative, from the first derivative, basically we're just taking the derivative of the given graph. So the given graph, it's a pretty simple graph, looks like a quadratic, but basically what we need to do is figure out what the slopes are in this graph in order to make a derivative graph of this graph, okay? So try to forget about the fact that we're making a double derivative from a single derivative, f double dash from f dash. Just think of it as like, okay, we're going to take a function f and we're going to find the derivative function of it, because it's basically the same thing, okay? At this stage anyway. So let's look at this, and we'll look at the different slopes we see here, slopes of tangent lines. And basically what we see is we see positive slopes going up here, and then here we have a zero slope, and then we have negative slopes going down. So it's a pretty simple derivative graph that we're going to draw from here. Basically we're going to have like positive numbers, and then when we get to x equals q, it becomes 0, and then we're going to have negative numbers. So basically the simplest graph we could draw that would be first positive, then 0, and then negative would be a straight diagonal line, kind of like that, right? So that would be the simplest possible graph we could draw based on the slopes here for f dash, okay? That wasn't so bad. Then we go down here and it says complete the table for the graph of y equals f of x. So now they would like us to figure out what f of x looks like based on specifically f dash, right? So from f dash we can see that in this part of the graph f dash is negative, right? And in this part of the graph f dash is positive. So basically what that means is that f goes down in this region, and then when it gets to this region it goes up, and then in this region it goes down again. And what are these dividing points? It basically would be P and R, right? So to the left of P, the f dash graph is negative, right? So if the f dash graph is negative, that means that the slope of f is positive. So here is my f graph that I'm drawing here. And I'm going to draw my f going down because this is negative values for the slope of f. And then here there's positive values for the slope of f, so my f graph's going to go up. And then here's negative values of the f dash graph again, so it's going to go down. So basically my f function looks like this. It's going to go down, it's going to go up, and it goes down. And where is its maximum point? It would be here at R, the maximum point, and the minimum point would be P, okay? Basically, P and R are x coordinates, right? We don't know the y coordinates. So then here in the table, it asks us what the maximum point of f, where is it? And it's asked for the x coordinate. The x coordinate, like we said, it's going to be R for the maximum point. Then it asks us for the inflection point of the function. And the inflection point of the function, of course, is given by when the second derivative is 0. When is the second derivative equal to 0? It's equal to 0 when x equals q. Okay? So those are the two answers for that. Then it asks us to justify your answer to part B2. Basically, that's just what we just said. If the second derivative equals 0, then you have an inflection point. F has an inflection point. Okay? All right. Next page. Oh, there is one weird case where even if you have a second derivative of 0, you might not have an inflection point. Remember, an inflection point on a sign diagram for the second derivative would have a 0 here, and then it would be like positive here and negative here in terms of concavity. There are some weird graphs where you have positive concavity on both sides and then you have 0 in the middle, or you have negative concavity on both sides and then you have 0 here. So you might want to also say that, okay, f double dash equals 0, and to the left of the inflection point we have f double dash is greater than 0, and to the right we have f double dash is less than 0. So you might want to add that too, just to take care of the weird cases, okay? Here's number 2. On the axes below, sketch a curve y equals f of x, which satisfies the following conditions. Basically, it gives us a function here, but they only give us 2 points. The 2 points they give us are 0, -1, and 1, 2. They're marked right here. So we know that the function goes through these 2 points. We're trying to figure out what else we know about the function. So first thing it says is that between x equals -2 and x equals 0, the slope is negative. Okay, so between -2 and 0, we know that it goes down, so it kind of goes down like that, right? We won't look at the second derivative yet, okay? And then it goes through this point here. And then between x equals 0 and 1, we know that the slope is positive. So we know it's going to go kind of like that to get to here. And then it's going to go through 1, 2. And then between 1 and 2, we know that the slope is positive. So it is going to continue to go up. So basically, the function kind of looks like that. Now what we need to do is look at the curvatures to see if it curves cupped up or curves cupped down. And so from -2 to 0, which is starting here, so I was irresponsible to draw that so far to the left, right? So starting at -2, we know that the curvature is cupped up. So we know that it's going down and cupped up, so we know it looks kind of like that, right? And then between 0 and 1, we know not only it's going up, but we also know that it's cupped up, so we know that it kind of goes like that. Okay, it looks like that because it's cupped up. Cupped up means it goes like that, right? And then from 1 to 2, we know that it's going up, but it's cupped down. So that means it's kind of going like that, and we know what it's doing up until it gets to 2, and after that we don't know what it's doing. So I'm just going to draw it like that. We know that it's going up, and we know that it up to x equals 2, it's cupped down. Okay, after that we don't know. So we're just going to draw that much of it. And we actually don't know what this point is, and we don't know what this point is. It's just a sketch. Okay? So what should you have marked? You should have it going through here. You should have it going through here. You should have this connecting the 2 points with a cupped up curvature. And then you should have a cupped up curvature here, and the curve should be going down, and this curve should be going up, and it should be cupped down. So that's what you can gather from this table here. Okay, next question. Number 3, the diagram below shows the graph of f of x equals x squared e to the -x for the interval from 0 to 6. These are the points of inflection at A and C, and there is a maximum at B. So A and C, these are inflection points, and B is a maximum, which it surely looks like one. Using the product rule for differentiation, find f dash of x. So the first thing we're going to do is we're going to find the derivative of this function here. Let's see, if we have x squared e to the negative x, that's a product. So let's say that x squared is u and e to the negative x is v. Then u dash is going to be 2x and v dash is going to be negative e to the negative x. So if we do product rule on this, we will get that f dash is equal to x squared, which is u, times v dash, which is negative e to the negative x, and then we're going to add that to v, which is e to the negative x, times u dash, which is 2x. And so if we rearrange that, we could write 2x e to the negative x minus x squared e to the negative x. Okay, so that is f dash, and we could simplify that a little bit if we wanted to. We could, or not necessarily simplify, but we could factor out some stuff that would give us x e to the negative x times 2 minus x. I don't know if that's better or worse, but we'll write that here. So x e to the negative x, 2 minus x, that is our expression for f dash. Then it says find the exact value of the y-coordinate of b. So for this one here, it is asking us to find the y-coordinate of the maximum point. So how do we know where the maximum point is? We know where the maximum point is by setting the derivative equal to 0. So if we set the derivative equal to 0 here, we can see that there's a couple ways for this expression to be 0. First of all, this x might be 0, and this x might be 2. Those are the two obvious ways that this expression could become 0. So I would assume that the x equals 0 point is the point right here, and the x equals 2 point must be this point here, because remember, f dash equals 0 are all the places where this function has a slope of 0. This must be one of them, and this must be the other one. So our b point is at x equals 2. So if we want to know what the y value is for b, then all we need to do is substitute 2 into the original function of x squared x e to the negative x. So f of 2 is equal to 2 squared times e to the negative 2, which is 4e to the negative 2, which is equal to 4 over e squared. So we could write that here. So that would be b. And then it says the second derivative of f is, and they just give it to us here, okay? Why are they giving it to us? Use this result to find the exact value of the x-coordinate of c. Okay, so they're giving us the second derivative because they want us to find this inflection point here by using the second derivative. How do we find the inflection point using the second derivative? We just set it equal to 0. So the f double dash is going to be x squared minus 4x plus 2 e to the negative x equals 0. So when is this equal to 0? Well, remember, e to the negative x is never equal to 0. So here also there's no x which causes e to the negative x to become 0. So we just ignored that. And we're going to ignore this here. So the only possibility is that x squared minus 4x plus 2 might be 0 sometimes. And so that is just a quadratic equation, right? So maybe there is a whole number solution here if we could factor it, but I'm pretty sure there's not because I don't see anything here that's obvious. So that means we're going to have to use quadratic formula, right? So it's going to give us x equals positive 4, which is negative b, plus or minus square root of b squared, so that would be 16, minus 4 times a, which is 1, times 2, all over 2. So that is basically equal to 2 plus or minus 16 minus 8 is in the root sign, so that would be square root of 8 over 2, which is equal to 2 plus or minus, and square root of 8 is equal to 2 times square root of 2, so that's equal to 2 plus or minus square root of 2. Okay, so the two the two inflection points are 2 minus square root of 2 and 2 plus square root of 2. Okay, and in this particular case, so this must be 2 minus square root of 2. Remember, square root of 2 is about 1.4, so that's about 0.6. That looks like it might be A. And then this one here would probably be 2 plus square root of 2, which would be about 3.4. Okay, so that means that the x-coordinate of C would be 2 plus square root of 2. Okay, last problem, number 4. Consider the curve y equals natural log of 3x minus 1. Let P be the point on the curve where x equals 2. Write down the gradient of the curve at P. Okay, so gradient of the curve at P, that is just another way of saying the derivative at a certain point. So why don't we take the derivative of y? So we'll get this natural log of something. So the derivative of natural log of something is 1 over something. And then we're going to use chain rule. So we're going to take the something and take the derivative of that, which would be the derivative of 3x minus 1, which is just 3. So that's basically equal to 3 over 3x minus 1, right? But we want the derivative at a specific point, which is x equals 2. So we're going to plug 2 in there, and then we get 3 over 3 times 2 minus 1, which is equal to 3 over 5. So the answer is just 3/5. Okay? Then it says the normal to the curve at P cuts the x-axis at R. Find the coordinates of R. Okay, so if you remember, if we have a function, and I don't know exactly what this function looks like, but it's natural log, so it kind of looks like this. And at some point, we have found that the derivative at x equals 2 is a line that is slope 3/5. Okay, and what they want us to do is they want us to, instead of finding the tangent line, they want the normal to the curve, which is going to cut that point, and then it's also going to hit the x-axis at some point. And they want to find out when this dotted line hits the x-axis. Well, basically, that's pretty easy to find out as long as we find the equation of this dotted line. Well, remember, look at your formula sheet and grab the point-slope form, because that's the most useful form to find tangent line equations and normal line equations. Basically, it's this form here. So what is the point we're going to use? The point we're going to use is x equals 2 and y equals something. Okay, so x1 equals 2, and then what is this point here? Well, we're going to find out by plugging 2 into that terrible looking equation there. It's going to be natural log of 3 times 2 minus 1, right? So that would be natural log of 6 minus 1, which is 5, natural log of 5. So y1 is going to be natural log of 5, x1 is going to be 2, and then our slope for the normal line is going to be the negative reciprocal of 3/5, because the tangent line and the normal line are perpendicular, right? So our m here is going to be actually 1 over 3/5, or negative 1 over 3/5, which is equal to negative 5/3, okay? So our m value is going to be negative 5/3, our x1 is going to be 2, and our y1 is going to be natural log of 5. So here is the equation of the line, which looks pretty awful because it's got natural log in it, and it's got a fraction, whatever, okay? But other than that, it's just a harmless equation of a line. And what we want to know is, where does this line intersect the x-axis, which means what is the x value when the y value is 0, right? Because at this point here, we know that the line goes through here, and we know that it's going to be something comma 0, right? Because it's an x-intercept. So we're just going to put 0 in for y, and then we're going to solve for x. And that'll give us the x-intercept of the normal to the curve. And so that'll be negative natural log of 5 equals negative 5/3 x minus 2. Let's take the negatives out by multiplying negative times both sides. Let's multiply 3/5 times both sides, and we'll get 3/5 natural log of 5 equals x minus 2. And then let's add 2 to both sides, and then we'll get 3/5 natural log of 5 plus 2, and that will be the x-intercept. Okay, that looks pretty horrible, but that's the answer here. And that's it.